Hello. In this video we're going to take a look at infinite dimensional Hilbert spaces, or rather we're going to reassess what we've already done and see that we've actually already been working with infinite dimensional Hilbert spaces when we've worked with functions. So we've had two schemes that we've worked with. The first is wave mechanics and the second is matrix mechanics. In the second we've had quantities like vectors and matrices. And we're familiar with how to manipulate these things when the dimension of the space in which we're working has a finite number of dimensions. In the case that we extend our space to have an infinite number of dimensions, the objects just become the following. Vectors become functions and matrices become differential operators. And in general we can use the overarching terms states, referring either to vectors in finite dimensional spaces or functions in infinite dimensional spaces, and operators referring to either matrices or differential operators. So this might seem a little bit abstract, thinking of a function, say, as an infinite dimensional vector, but there's a couple of reasons that it's quite natural. The first is if we think in terms of how a computer would display a function. That is, we would have to work with a discrete set of positions if the function is defined in position space, which would be stored as a vector of different points. And for each of those points, we'd have a value of our function. Now, if we want to approximate a smooth function, taking a value in a real domain, then we'd have to try and make the spacing of these points smaller and smaller, something like this. And as we take the limit of the number of points here going to infinity, and the spacing between each one being infinitesimal, we develop a smooth function. But of course the computer only ever works with a discrete set of points along the real line. It can't store an infinite set of numbers. It only has a finite memory. So in this sense you see that a function really is naturally an infinite dimensional vector because it has to take a value for each of an infinite number of real numbers of x. Another way to see in terms of matrices why this is that if you think of, we've been looking at eigenvalue equations for our matrices, and for an n by n matrix, the eigenvalues are found by a characteristic polynomial, and that characteristic polynomial has the form some coefficient times x plus another coefficient times x squared plus another coefficient times x cubed and so on up to x to the power of n. So it's an nth order polynomial. If we take the limit of the matrix becoming infinitely large, the polynomial that describes the characteristic equation has to have an infinite number of terms, an infinite number of different powers of x. But if you write a polynomial which has an infinite number of powers of x in it like that, what you've really written is a Taylor series which describes an arbitrary function. And we can always expand a function of x as a Taylor series like that, or there's a large set of functions for which we can expand it as a Taylor series. So your matrix then, the characteristic polynomial stops being an nth order polynomial, it becomes an infinite order polynomial, which is really just a function. So it's quite natural to think of it in this way. So in our finite dimensional vector spaces, we can define orthonormal bases defined as follows. That is, sets of normalised vectors such that the inner product of the vector with itself will give 1. This is the Kronecker delta, defined to be 1 when I equals j, or 0 when I doesn't equal j. So if ei and ej are the same, this is length 1, and if ei and ej are, I and j are different, then it's equal to 0. And this defines an orthonormal basis of vectors. In the infinite dimensional space, the equivalent to this is as follows. We define an orthonormal basis of states x, which are position states, and we say that if you have the inner product of x with y, that's equal to the Dirac delta function of x minus y. This is in one dimension of space. So remember, the Dirac delta function is really like a continuum limit of the Kronecker delta. It's equal to 0 if x doesn't equal y, and it equals infinity when x does equal y, but in such a way that an integral over it will give the value 1. So it's the natural generalization. So whereas we have a finite number of vectors which span a finite dimensional vector space, we must have an infinite number of these position vectors. But again, you can just think of this in terms of how a computer would store a set of real numbers. It would really approximate them as a finite number of points. So then it would be a finite dimensional vector space, and these would be the points along that space. So another relation we have in the finite dimensional case is that the identity matrix, which we can denote with this sort of blackboard bold 1, is equal to the sum from I equals 1 to n, where this is the dimension of the space, of the outer products of the normalized basis vectors. In the infinite dimensional case, the equivalent of this. So the identity now, which is really an identity operator, is equal to the outer product of the position states integrated now over x from minus infinity to infinity. So the integral is replacing the sum because we've taken the limit of the number of dimensions going to infinity. In the finite dimensional case, let's keep all the finite dimensional stuff to the side of the line, we can express any vector in the space as a sum from I equals 1 to n, the size of the space, the dimension of the space, multiplying the basis vectors of the space by some coefficient vi, and the coefficients vi are given by the inner product of the basis vector with the vector v. The equivalent in the infinite dimensional case is this. So let's denote, rather than choosing v for our finite dimensional vectors, we'll choose f for our infinite dimensional ones, because these are going to be functions, so call them f. And we can write them now as replace the sum with the integral. So it's some function of x multiplying the basis states x, and this function of x is defined to be the inner product of the x state, so the basis vector, with the function f. So this takes a bit of getting used to, but what we're saying here is that what we usually call as our functions of x are really some more abstract concept. They're an infinite dimensional vector projected into the x basis. So what other bases could they be projected into? Well, actually, they can be projected into other bases because we can write the function as a function of anything. It doesn't have to be a function of position. An example that we've actually seen already is that you can write your functions in momentum space. And what you would do mathematically to write a function in position as a function of momentum is carry out a Fourier transform. And that's built in naturally into this structure. So there's a more, the function is actually a slightly more abstract entity than the thing that's a function of x. The function could be a function of x or of p or of anything. So this ket notation indicates that the sort of true nature of the function before it's projected into a particular basis. We'll see a concrete example of this in a second. Another key generalization we have is this. So we have an inner product between our vectors, and remember it's a complex vector space. So the writing the ket backwards like this, the bra, is the Hermitian conjugate. And remember, a Hilbert space, which is what we're working with, is defined to be a linear vector space, but including an inner product, and having all the vectors that we're referring to be normalizable, so of finite length. And this generalizes quite nicely in the basis of functions as follows. So just as we can write the inner product of two vectors, u and v, like this, we can write the inner product of two functions, f and g, in exactly the same way. But to make it look more standard, we can use the trick of inserting the identity. Okay, so if we insert the identity between f and g, we have the following. We can always just put an identity between two vectors, but then we use this identity up here to rewrite this as follows. So an integral over dx, and we've inserted the complete set of outer products here. But then, according to our definition up here, x inner product with g, like this, is just g of x. And f inner product x, well, that has to be the Hermitian conjugate, sorry, the complex conjugate, because this is just a complex number now, because it's an inner product. So this has to be the complex conjugate of x inner product f. So it's as follows. So the equivalent to the inner product in the vector space is the integral from minus infinity to infinity over x of f star of x, g of x. Okay, so this is the inner product defined for functions. And in fact, we've used that implicitly when we were working with wave mechanics earlier on in the course. So the most important example of an infinite dimensional vector that we're likely to encounter is the following. Psi of x, the wave function, which we've been using in the wave mechanics part of the course, in terms of matrix mechanics, is just the ket psi projected into the x basis. But we could equally well have projected it into the momentum basis, in which case we would have psi of p instead. So we sometimes write this as psi twiddle, and that's the Fourier transform of psi of x. Okay, so psi, the ket, is really a slightly more general object. It's what lies at the heart of the function before you say it lives in the x basis or the p basis or whatever other basis you want to work in. So a really important result we'll have, it's just re-expressing something we already know, is as follows. So we start from our resolution of the identity, written in the position basis, and then we can sandwich this with states psi from the left and right. So I've just brought a bra psi from the left, a ket psi from the right, and on the right here I've done the same. The state psi is not itself a function of x, so it can go through the integral. It can be projected into the x basis, which is what's happening here, but the ket psi is not basis dependent. And so then this object is psi of x, as we've just said, and this object must be psi star of x, the complex conjugate. So this is nothing other than the modulus square of psi of x, and the psi's sandwiching the 1 here. The 1 can just disappear because the identity operator acting on a state is just the state. So we have the result. Psi inner product psi is just equal to the integral over x of modulus psi squared. But we know that this thing equals 1. This is just our normalization of the wave function. The particle, while we don't know where it exists, must exist somewhere. And so the integral of the probability density across all of space is equal to 1. And so we see that in terms of vectors, in terms of the infinite dimensional Hilbert space expressed as these states, we see that the state is of length 1. So quantum states are complex vectors of length 1, and vector here is used in the more general sense, where it could also be the ket form of a function before projection into a particular basis. Okay, thank you for your time.